In morning of 7:42, March 14, 1941, Beatrice Schilling stood on the airfield at RAF Kenley observing a Hurricane pilot enter his cockpit for what could be his final mission. At 32 years old, with 6 years at the Royal Aircraft Establishment, she had found zero solutions to the problem that was costing her pilots their lives. The Luftwaffe had dispatched 43 Messerschmitt Bf-109 fighters across the channel that week. RAF pilots had engaged them in 27 separate dogfights. 14 Hurricanes had been shot down. 9 Spitfires. The pattern remained consistent. British pilot spots German fighter. British pilot initiates a dive to attack. Engine cuts out. German fighter escapes. Or worse, German fighter circles around and fires upon the stalled Hurricane while the pilot struggles desperately to restart his Rolls-Royce Merlin engine. Schilling had reviewed the combat reports. She'd examined the maintenance logs. She'd interviewed pilots who'd survived the engine failures. The carburetor flooded during -G maneuvers. Simple physics, devastating consequences. When a Spitfire or Hurricane entered a sudden dive, fuel rushed to the top of the float chamber. The engine starved. The engine died for 1.5 seconds. 1.5 seconds was sufficient time for a Messerschmitt to close 300 yards in open fire. The Germans didn't face this issue. Their Daimler-Benz engines utilized direct fuel injection. No float chamber, no flooding. Bf-109 pilots could dive, climb, roll, invert their aircraft without losing power for even a moment. This provided them with a decisive advantage in every engagement. British pilots were aware of it. German pilots capitalized on it. Squadron commanders documented it. And the Royal Air Force was losing experienced pilots faster than training schools could replace them. Schilling had dedicated 11 months to addressing the problem. The engineering teams at Rolls-Royce were developing a pressure carburetor, a proper solution, a complete redesign of the fuel delivery system. But the pressure carburetor wouldn't be available until 1943, possibly 1944. The war couldn't wait. The pilots couldn't wait. Every morning, young men climbed into Spitfires and Hurricanes, knowing their own engines might kill them before the Germans had the chance. Squadron leader Davies passed Schilling heading toward the Hurricane. 24 years old, 41 combat missions, 3 confirmed kills. He'd reported engine failure twice in the previous month. Both instances during combat dives. Both times he'd survived through sheer luck and 3,000 hours of training. He nodded at Schilling. She nodded in return. He didn't know she was the carburetor specialist from Farnborough. He likely assumed she was someone's secretary. If you want to see how Schilling's breakthrough saved RAF pilots, please hit that like button. It helps us share more forgotten stories from the war. Subscribe if you haven't already. Back to Schilling. She'd brought something with her to Kenley that morning. A small brass component, precisely machined, remarkably simple. Her team at the Royal Aircraft Establishment had tested it on a bench engine for 6 weeks. It functioned. But bench tests weren't combat. Combat was 300 miles per hour. Combat was -G forces powerful enough to pin a pilot against his harness. Combat was life or death in 1.5 seconds. Schilling walked to her Norton motorcycle. In her leather satchel was the brass restrictor, and a plan that would either save the Royal Air Force or terminate her career at Farnborough. By noon, she'd know which. The carburetor problem had begun in July 1940. The Royal Air Force had transitioned to 100-octane fuel. Higher octane meant more boost. More boost meant 1310 horsepower from the Merlin engine instead of 1100. The Spitfire Mark II could reach 370 miles per hour in level flight, fast enough to catch Messerschmitt 109s. But the Skinner's Union carburetor couldn't handle the -G forces that accompanied high-speed combat maneuvering. Schilling understood carburetors better than anyone at Farnborough. She joined the Royal Aircraft Establishment in November 1939, 1 month after war was declared. She was one of 2 women in the engine department. The other woman was a secretary. Schilling was principal technical officer responsible for carburetor research and development. Most of the men she worked with had never encountered a female engineer. Some of them didn't believe women belonged in engineering. Schilling wasn't concerned with their beliefs. She cared about keeping pilots alive. She'd grown up disassembling engines. At 14, she'd purchased her first motorcycle, a Norton. She'd dismantled the 2-stroke engine down to individual components, learned how every part functioned, then reassembled it. At 25, she'd raced that Norton at Brooklands, averaging 106 miles per hour, fast enough to earn the British Motorcycle Racing Club Gold Star. Only 3 women in history had earned that award. Schilling was the second. Racing had taught her how engines failed under stress. High G turns, sudden acceleration, extreme lean angles. She'd learned to sense what an engine needed before the gauges indicated it. That intuition had made her the finest carburetor specialist in Britain. And now British pilots were dying because their carburetors couldn't withstand combat stress. The solution had occurred to her in January. Simple physics. The float chamber flooding occurred because fuel could flow unrestricted when gravity reversed. What if you restricted the flow? Not completely, just enough to prevent flooding. The engine would still receive fuel, just not excessive fuel. A brass disc with a precisely calculated hole in the center. Install it in the fuel line before the carburetor. Limit maximum fuel flow to slightly less than what the engine demanded at full throttle. She'd machined the first restrictor herself. Brass thimble-shaped, 0.125 inches in diameter. The hole in the center was 0.04 inches. Those dimensions were critical. Too large and the carburetor would still flood. Too small and the engine would starve at full power. She'd tested 17 different sizes before finding the correct one. Then she'd simplified the design. A flat washer was easier to manufacture, easier to install, easier to replace if damaged. Bench tests indicated it worked. The restrictor prevented flooding during simulated negative G conditions. But bench tests weren't combat. She needed to test it on an actual aircraft under actual combat conditions. The challenge was obtaining permission. Installing unauthorized modifications on RAF fighters violated approximately 40 different regulations. If the restrictor failed in combat and a pilot died, Schilling would be court-martialed, possibly imprisoned. She decided to bypass permission and request forgiveness later. That morning at Kenley, she had 6 restrictors in her satchel and one very cooperative ground crew sergeant who owed her a favor. Sergeant William Cooper had worked on Merlin engines for 3 years. He'd witnessed 19 pilots die from engine failures. He didn't ask questions when Schilling showed him the brass washer. He simply nodded and reached for his toolkit. The Hurricane sat on the dispersal pad. Pilot inside. Engine warming up. 20 minutes until takeoff. Cooper worked quickly. He disconnected the fuel line between the pump and carburetor. The restrictor slid into position. He secured it with a small butane torch. 60 seconds of work. The modification was invisible unless you knew where to look. Schilling inspected the weld. Clean, solid, professional. Squadron Leader Davies would fly with the restrictor. He was unaware it was there. Schilling hadn't informed him, hadn't told the squadron commander, hadn't told anyone except Cooper. If the restrictor failed and Davies died, there would be no paper trail, no authorization forms, no testing documentation, just a dead pilot and a brass washer that shouldn't have been there. The Hurricane's Merlin engine roared to full power. Davies conducted pre-flight checks. Oil pressure good, coolant temperature good, magnetos firing on all 12 cylinders. He released the brakes. The Hurricane rolled forward, gained speed, lifted off. Schilling watched it ascend. 800 feet, 1,200 feet, 2,000 feet. The Hurricane banked south toward the channel. She'd brought a pair of binoculars. She watched Davies climb to 15,000 feet. 2 more Hurricanes joined him, a section of 3, standard patrol formation. They flew toward Dungeness. German fighters had been active over Dungeness all week. If Davies encountered a Messerschmitt, he'd have to dive and the restrictor would either work or it wouldn't. Schilling waited on the tarmac. Cooper stood beside her. Neither spoke. Ground crew prepared 2 more Hurricanes for the afternoon patrol. A fuel truck rumbled past. Mechanics shouted technical terms across the dispersal area. Normal sounds of a fighter station at war. Schilling heard none of it. She was calculating fuel flow rates in her mind. 0.04 inches. Maximum flow at full throttle. Negative G duration 1.5 seconds. The calculations worked, but math wasn't combat. 40 minutes passed. An hour. Radio silence from Davies' section. That could mean anything. No contact with enemy fighters or contact so intense there was no time to report or Davies was dead and his Hurricane was scattered across a French field. At 0937, the radio crackled with the controller's voice. 3 Hurricanes inbound, 2 minutes out. Schilling raised the binoculars. She saw them. 3 dark shapes against the morning sky. All 3 aircraft. No losses. The Hurricanes entered the circuit. Davies landed first. He taxied to dispersal, shut off the engine, climbed out. Schilling walked toward him. Her hands were trembling. She'd designed bombs before. She'd tested engine modifications under laboratory conditions. She'd never done anything like this. Never installed an unauthorized modification and sent a pilot into combat to test it. Davies removed his helmet. He was smiling. That was unusual. Pilots didn't smile after combat patrols. They usually looked exhausted, haunted. Davies appeared excited. Cooper asked the question. "Any problems with the engine, sir?" Davies looked at Cooper, then at Schilling, then back at Cooper. "Best the Merlins ever run," he said. "Dove on 2 Messers over Dungeness. Engine never missed a beat." Schilling asked Davies to describe exactly what happened. He'd spotted 2 Messerschmitt 109s at 14,000 feet, both aircraft flying east toward France. Davies had positioned his section above them. Altitude advantage. He pushed into a steep dive, 400 miles per hour. Negative G-forces strong enough to lift him against his harness straps. The dive that should have killed his engine, but the Merlin kept running. Full power throughout the entire dive. Davies had closed to 200 yards before the German pilot spotted him. He'd fired a 3-second burst, observed hits on the left Messerschmitt's wing route. The German fighter turned sharply right and fled toward France. Davies had pulled up, climbed back to altitude. The engine had performed flawlessly. It was the first time in 11 months that Davies had successfully executed a diving attack without his engine cutting out. He wanted to know what maintenance had done to his Hurricane. Schilling told him. She explained the restrictor, the brass washer, the fuel flow limitation. Davies stared at her for 5 seconds. Then he turned to Cooper. "Put that thing in every Hurricane on this station," he said. "Today." Schilling explained it wasn't authorized. Davies didn't care about authorization. He cared about surviving combat. Every pilot at Kenley had lost friends to engine failures. 19 pilots dead in 6 months. Davies said if the brass wanted to court-martial him for installing an unauthorized modification, they could do it after the war. Right now, his squadron needed functioning engines. Cooper installed restrictors in 4 more Hurricanes that afternoon. Schilling had brought 6. She kept 1 for testing. 5 Hurricanes flew combat patrols with restrictors over the next 3 days. 0 engine failures. 12 diving attacks successfully executed against German fighters. Pilots reported the Merlin engines ran perfectly, better than perfectly. Some pilots claimed they were getting more power at altitude. Word spread rapidly. By March 18th, every squadron commander in 11 Group knew about the restrictor. They wanted it, all of them. Immediately, Schilling received 14 phone calls in 2 days. Could she visit their stations? Could she bring more restrictors? How quickly could they be manufactured? The challenge was supply. Schilling had machined 6 restrictors herself in the RE workshop. Manufacturing thousands would require proper production facilities, brass stock, precision machining equipment, quality control. She needed approval from the Air Ministry. She needed funding. She needed time. She received approval in 4 days. The Air Ministry fast-tracked her proposal. A war-winning modification, they called it. Rolls-Royce received the production contract. They could manufacture 500 restrictors per week. Installation would begin immediately at every fighter station in Britain. Schilling assembled a small team, 3 engineers from Farnborough, 2 civilian mechanics. They would tour RAF stations and supervise installation. The restrictor could be fitted without removing aircraft from service. That was crucial. Every Hurricane and Spitfire needed to remain operational. The Battle of Britain was technically over, but German fighters still crossed the Channel daily. RAF Fighter Command couldn't afford to ground its squadrons. Schilling loaded her Norton motorcycle with tools and restrictors. She'd visited 43 RAF stations before the war. She knew every fighter base in southern England. She knew the commanding officers. She knew the ground crews. Now she'd visit them again, this time with a brass washer that would save their pilots. By March 25th, installation teams were ready. 600 restrictors manufactured, 40 stations on the schedule, 3,000 Merlin engines awaiting modification. Schilling started her Norton and headed north toward Biggin Hill. Biggin Hill was the busiest fighter station in 11 Group. 32 Spitfires, 21 Hurricanes, for squadrons rotating through continuous combat operations. Schilling arrived at 0800 on March 26th. Station Commander Group Captain Grace met her at the gate. He'd lost 7 pilots to engine failures in the previous 2 months. He wanted the restrictors installed immediately. The ground crews worked in shifts, for aircraft at a time. Each installation took 12 minutes. Disconnect fuel line. Weld restrictor in place. Reconnect line. Test for leaks. The welding had to be perfect. A faulty weld at altitude could completely starve the engine. Schilling supervised every installation personally. She inspected every weld, tested every connection, rejected 3 restrictors that didn't meet specifications. Pilots watched the modifications with intense interest. Flight Lieutenant James Lacey had 41 combat missions. He'd experienced engine failure twice, both times during critical moments in dogfights. He asked Schilling how a simple washer could solve the complex carburetor problem. She explained fuel flow physics, float chamber dynamics, negative G effects on liquid fuel. Lacey understood immediately. He was an engineering graduate from Cambridge. He called it brilliantly simple. By March 28th, all 53 Merlin engines at Biggin Hill had restrictors installed. Schilling moved to Hornchurch, then North Weald, then Tangmere. The pattern repeated at every station. Ground crews worked 12-hour shifts. Pilots flew combat patrols with modified engines. 0 failures reported. The restrictor functioned exactly as designed. Pilots began calling it Miss Schilling's orifice. The nickname originated from Sir Stanley Hooker, chief engineer at Rolls-Royce Supercharger Division. It was crude British humor, somewhat inappropriate. Schilling didn't mind. She'd spent 6 years working with RAF personnel. She understood how military men coped with stress. If crude nicknames helped them remember the modification, she'd accept any name they wanted to use. The nickname spread faster than the restrictor itself. By April, every pilot in Fighter Command knew about Miss Schilling's orifice. They specifically requested it. Some pilots refused to fly combat missions until their aircraft had the modification installed. Squadron commanders supported them. They'd witnessed too many good pilots die from preventable engine failures. German intelligence noticed the change in British fighter performance. Luftwaffe after-action reports from early April mentioned improved RAF diving attacks. British fighters no longer broke off pursuit during negative G maneuvers. Messerschmitt pilots could no longer exploit the carburetor weakness. The tactical advantage had vanished. By mid-April, Schilling's team had installed restrictors in 2,100 Merlin engines, every Hurricane and Spitfire in fighter command, every operational training unit, every aircraft in reserve status. The modification became standard equipment. New aircraft rolling off production lines at Castle Bromwich and Southampton came with restrictors pre-installed. The pressure carburetor was still in development. Rolls-Royce estimated it would be ready for production in 1943, but the restrictor worked so well that some engineers questioned whether the pressure carburetor was even necessary. Why redesign the entire fuel system when a 50-cent brass washer solved the problem? Schilling knew the answer. The restrictor was a stopgap, a brilliant stopgap, but temporary. The pressure carburetor would eliminate the negative G problem completely. No fuel flow restrictions, no power limitations, full engine performance under any flight condition. That was the proper engineering solution. But until 1943, Miss Schilling's orifice kept RAF pilots alive, and that was sufficient. The results were quantifiable. Fighter Command tracked combat statistics meticulously. Every engagement, every kill, every loss, the numbers told a clear story. March 1941, before the restrictor, RAF fighters reported engine failures in 38% of diving attacks against German aircraft. Pilots broke off pursuit. Enemy fighters escaped. Or worse, German pilots recognized the weakness and exploited it. They deliberately lure British fighters into diving attacks, knowing the Merlin engines would fail. April 1941, after the restrictor, engine failures during diving attacks dropped to 0.4%, almost non-existent. The few failures that did occur were unrelated to the carburetor. Mechanical problems, battle damage, normal combat attrition. The kill-to-loss ratio improved immediately. March had been brutal. Fighter Command lost 47 Hurricanes and Spitfires in combat. Shot down 61 German aircraft, a ratio of 1.3 to 1, barely breaking even. April was different. 29 British fighters lost. 94 German aircraft destroyed, a ratio of 3.2 to 1. The restrictor wasn't the only factor, but squadron commanders credited it as a major contributor. Pilots reported increased confidence in combat. Flight Lieutenant Robert Stanford Tuck flew Spitfires out of Duxford. He'd experienced engine failure 4 times before the restrictor. After installation, he executed diving attacks without hesitation. He destroyed 3 Messerschmitt 109s in May, 2 more in June. He credited the restrictor with giving him the confidence to commit to aggressive tactics. The modification extended beyond Fighter Command. RAF Coastal Command requested restrictors for their Beaufighters. Bomber Command wanted them for training aircraft. Even the Fleet Air Arm inquired about installation on carrier-based fighters. Schilling coordinated production with Rolls-Royce. By June, they were manufacturing 1,000 restrictors per week. The restrictor remained in service through 1943. Rolls-Royce finally introduced the pressure carburetor in January 1943. The new carburetor eliminated the negative G problem completely. It used fuel injection principles similar to German engines. No float chamber, no flooding, perfect fuel delivery under any flight condition. But converting existing aircraft to pressure carburetors required extensive modifications. Remove the old carburetor, install new fuel pumps, rewire engine controls. Each conversion took 8 hours. During those 8 hours, the aircraft couldn't fly combat missions. Fighter Command couldn't afford to ground squadrons for extended maintenance, so they kept the restrictors. Many aircraft flew with Miss Schilling's orifice until 1944, some until the end of the war. New production Spitfires and Hurricanes received pressure carburetors, but older aircraft retained their restrictors. Pilots trusted them. Ground crews knew how to maintain them. If it worked, don't change it. Schilling moved on to other projects. She worked on cold weather starting systems for engines in Iceland and Russia. She researched high-altitude fuel mixture problems. She helped design improved supercharger systems for late-war Merlin variants. The Royal Aircraft Establishment kept her occupied with dozens of technical challenges. But the restrictor remained her most renowned contribution. Pilots remembered it. Engineers studied it. After the war, aviation schools taught it as an example of elegant problem-solving under pressure. Simple solution, immediate implementation, measurable results, everything good engineering should be. Keith Maddock, chief engineer at Hangar 42 during the war, said it years later. Beatrice Schilling helped us win World War II. Of that, there is no doubt. The restrictor was a war-winning modification. Schilling's work didn't stop with the restrictor. The Royal Aircraft Establishment had dozens of critical problems that required solutions. Engine failures at high altitude, fuel system icing in extreme cold, starting problems in Arctic conditions. Every problem threatened pilot lives. Every problem landed on Schilling's desk. She worked on cold weather modifications for Spitfires deployed to Murmansk. Russian winter temperatures dropped to -40 degrees Fahrenheit. Standard engine oil turned to sludge. Batteries died. Fuel lines froze. British pilots couldn't start their aircraft. Soviet ground crews had no experience with Merlin engines. Schilling developed a cold start procedure using preheated oil and modified fuel mixtures. It worked. Spitfires flew combat missions over Murmansk through the winter of 1941. She researched high-altitude performance problems. Late-war Spitfire variants flew at 35,000 feet. The Merlin engine struggled at that altitude. Thin air, low oxygen content, fuel mixture had to be precisely calibrated. Too rich and the engine flooded. Too lean and it overheated. Schilling developed altitude-compensating carburetor modifications that improved power output by 8% above 30,000 feet. Her personal life remains separate from her work. She'd married George Naylor in September 1938. He worked at the Royal Aircraft Establishment as an aerodynamicist. When war started, he'd volunteered for RAF Bomber Command. He flew Avro Lancasters with 625 Squadron, completing 31 combat missions over Germany. He earned the Distinguished Flying Cross for completing an extra tour beyond his required missions. Schilling worried about him every time he flew. She understood bomber loss rates. Bomber Command suffered higher casualties than any other RAF branch. 1 in 2 bomber crew members didn't survive the war. Naylor beat those odds. He survived his tours and returned to Farnborough in 1944. They never discussed his missions. He never asked about her projects. They kept work and marriage in separate compartments. Schilling continued racing motorcycles when time permitted. She'd stopped racing at Brooklands when war started. The famous circuit had been converted to aircraft production facilities, but she still rode her Norton. Fast riding helped her think, solve problems that laboratory work couldn't resolve. Some of her best engineering ideas came while riding at 90 miles per hour on country roads. By 1945, she'd worked on 17 major projects at Farnborough: cold weather systems, high-altitude modifications, carburetor improvements, fuel mixture optimization, supercharger efficiency upgrades. Each project saved lives. Each project kept RAF aircraft operational under extreme conditions, but none achieved the fame of the restrictor. The war ended in May 1945. Germany surrendered. Japan followed in August. The Royal Aircraft Establishment transitioned from wartime emergency projects to peacetime research. Slower pace, lower urgency, different priorities. Schilling stayed at Farnborough. She had no intention of leaving. Engineering was her life. In 1948, she received official recognition for her wartime contributions. King George VI appointed her Officer of the Order of the British Empire. The OBE ceremony took place at Buckingham Palace. Schilling wore her formal dress, accepted the medal, posed for photographs, then returned to work at Farnborough the next morning. She never stopped engineering, never stopped solving problems, never stopped proving that women belonged in technical fields. Her career at the Royal Aircraft Establishment continued for another 21 years. But the restrictor remained her legacy, the brass washer that saved the Royal Air Force. Schilling worked at the Royal Aircraft Establishment until 1969. 33 years of continuous service. She never reached the top administrative positions. Those roles were reserved for men. The RAF leadership structure didn't promote women to director-level posts regardless of accomplishment. Schilling accepted this limitation. She preferred hands-on engineering work anyway. Laboratory testing, field modifications, real problems with real solutions. Her post-war projects included the Blue Streak missile program, Britain's first ballistic missile. Schilling worked on fuel delivery systems and high-altitude performance. She researched wet runway braking effects for jet aircraft. Landing accidents killed more pilots than engine failures by the 1950s. Understanding how water on runways affected tire friction could save lives. Schilling published 3 technical papers on the subject. She even helped design a bobsled for the Royal Air Force Olympic team. Strange project for an aeronautical engineer, but bobsled design involved aerodynamics, weight distribution, and friction management skills Schilling had mastered over 30 years. The RAF team used her bobsled design in competition. They didn't win medals, but they didn't crash either. Schilling retired in 1969 at age 60. She spent retirement restoring vintage motorcycles, racing occasionally at classic motorcycle events, maintaining her Norton. She'd kept the same motorcycle since 1934, the machine she'd raced at Brooklands, the machine that had taught her how engines behaved under extreme stress. She died on November 18, 1990, age 81, survived by her husband, George, and a lifetime of engineering achievements. The obituaries in British newspapers focused on the restrictor, the brass washer, Miss Schilling's orifice. Everything else she'd accomplished was footnotes. Her legacy lived on in unexpected ways. In 2011, a pub in Farnborough was renamed the Tilly Schilling. The Brooklands Museum purchased her racing trophies and badges in 2015. Winchester Heritage celebrated her in 2018 as one of Hampshire's extraordinary women. In 2019, Royal Holloway University opened the Beatrice Schilling Building for electronic engineering students. On March 8, 2019, the mayor of Waterville unveiled a plaque at the local library 110 years after her birth. The restrictor itself became a teaching example. Engineering schools worldwide studied it. Simple solution to complex problem. Immediate implementation under wartime pressure. Measurable, life-saving results. Everything good engineering should achieve. Some universities kept original restrictors on display. Small brass washers in museum cases. Reminders that elegant solutions don't require complexity. If this story moved you the way it moved us, do me a favor, hit that like button. Every single like tells YouTube to show this story to more people. Hit subscribe and turn on notifications. We're rescuing forgotten stories from dusty archives every day. Stories about engineers who saved lives with brass washers and brilliant thinking. Real people, real heroism. Drop a comment right now and tell us where you're watching from. Are you watching from Texas, Germany, United States, Japan? Our community stretches across the entire world.